Okay, we are live. Uh yeah, so today is the second, or third day of interview prep series, so to speak. So yesterday I went through linked lists and like stacks and queues and had a good refresher on pointers, which was a headache. And I was really happy to have my close friend to help me out to let me know what's wrong. So I was chatting with him for quite a bit, and I was glad to have gone through that. I think here on out, whenever I see a pointer, life will be much easier. It makes more sense. So today, I'm gonna be quite ambitious. I'm gonna try to finish the entire chapter here. So this includes binary trees, hashing. I think there's a part on specialized, something like priority queues or something like that. So without further ado, let's just get started. Okay. Okay. So where was I yesterday? Yesterday I was here, right? So using linked list doubly and singly, sorted and unsorted to think about how fast it takes to do things like search, insert, delete, that sort of stuff, finding maximum, minimum, predecessor, and successors. So that's good. Okay, now let's look for binary trees. Actually, I've worked the first time I think I did a very long stream. This was months ago. I don't think it's even on this channel. I did what I basically implemented the basics of binary search tree, and it took me 6 hours because I was an idiot. And I didn't know you could just delete things, for example, or that you could use like a like a dummy node, which is a super useful trick when it comes to these things. And I was trying to keep everything intact without adding or taking away anything, which is completely unnecessarily complicated and convoluted. Okay, so let's go. Enough chit chatto. We have seen data structures, not as okay. Yes, binary search trees. I don't know if this is easy for you guys to read if you guys are ever watching this, but I'm guessing it's not. So okay, maybe let's just do a single page view. Even though I don't know why you would be really watching this. Like you might be playing this for some reason, but to read along that is strange. Okay, whatever. Okay, let's just keep going. So two elements. The median elements above and below the given node. I should open up my iPad for this. I should be jotting down notes here. Why am I not doing this already? Okay. Let's okay. Okay, let's keep going. A linked list with 2 pointers per node. Okay. Together with 2 rooted binary trees called left and right subtrees. Okay, yeah, so a binary tree is basically a tree that splits into left or right, where you split two times at most. Yes, so every layer you have all these, so yeah, you could split in this fashion. Okay. Binary search tree. Wait, so no. Root. Left and right subtrees. The order among brothers node matters in rooted trees. So left is different from right. Gives the shapes of 5 distinct trees that can be formed for 3 nodes. Okay, like this, like this, like this, like this. Rooted. So if it's rooted, it matters. Okay, doesn't matter. I think we just move fast, and then when we hit a wall, then we bounce. Right? Okay, let's see how that works out. Okay. For Okay, this is interesting. So this means that if you have a binary search tree, everything on the left side should be less than the node, and then everything on the right side should be more than, and this gives you one unique definition of a tree. The allowable labelings for tree node trees are given in 3.2. Okay, so okay. Yeah, so if it's less, it has to go to the left. So if it goes 3 first, then 1, then 2, and 1, 2, 3, 1, 3, 2, 1, 2, 3. Okay, fair. Okay. An optional parent pointer. Okay, and a data field. Okay. Okay. Parent. Okay, so parent is optional. And again, these are pointers. So you get a pointer to the parent, not the parent itself. Tiny bit confusing, but I think at this point we need to just get used to this. Okay. So searching a tree. So if it's less than, you go to the left. Oh, sorry. Yeah, if the data is less than what you want, you go to the left. Otherwise, you go to the right. And you could do it recursively. So if L items, you return L. So L is a pointer to the tree. And you have the item type, which is the data. So if L is null, meaning you are done with the tree and it's not there, you null. If the item under that pointer is X, you return the pointer itself. And then if it's less than, you go to the left, otherwise you go to the right. This is okay, this is easy. H time, where H denote the height of the tree, right? So okay, yeah. So the height would be yeah, so each layer you have, you know, at most 2 to the H or 2 to the H minus 1, whatever. Number of nodes at most, yeah. So if you're finding minimum, meaning you go all the way left, and then right will be max. I mean, max will be go all the way to the right. Okay, so you get a tree, and the tree, pointer. Let me write this down first, so in case yeah. So find minimum. So you point. You take a pointer to the tree. If t is equals to null, hold on. If the pointer is null, which is to say that, okay, otherwise, if it's not null, you min to the left. So that means there's a pointer as well. And then that's a pointer. Okay, so your pointer starts off at the tree, and then you just go left all the way. Okay, this is understandable. Traversal. Visiting all nodes provides to be an important component. Traversing. Okay. Yes. Yes. So you go to the left first, then go to the right. But in this definition that is recursive, you always go from increasing order. Right. So you go to the left, do whatever you want to do, print, whatever, then go to the right. And if it's null, you do nothing, I guess. Yeah. Okay, yeah. So if it's null, you do nothing. That's correct. I'm sure like going through these codes like this is, you know, is half the story as you need to practice it. But I think I'll get to that at the end of the chapter. Okay. And then we'll maybe fire up lead code at that point. Each item is processed once. So ON. N is the number of nodes. Fair. Change. Processing item use a pre-order traversal, post-order traversal. Okay. Okay, just keep that in mind that we have pre-order and post-order traversals when it comes to doing the how to say, doing the processes or whatever operations. Okay, insertion is a bit tricky. There is only one place to insert we must replace the null pointer. Actually, it's not so bad, right? Wait, hold on. Yeah, this insertion was the one that took me forever. Or is it deletion? I'm not sure. So if I insert, I just need to find. Hold on. Okay. We must replace the null pointer found in T after an unsuccessful query for the key K. What? The key. Hmm. Mm, the null pointer. The null pointer. Okay, let me think. Let me draw this out. Okay, let's see. I have this, and then I don't know, like this. Okay, so let's say I wanna insert. Yeah, okay, I see what you mean. So we just, let's say, I don't know, let's say this is 10. Let's say this is 10, 9. Well, I don't know, let's go with 5, 3, 9, 6, 8. And then this would be 12, 11, 20, 15, 40. And if you want to enter 16, it would be one of the bases. Okay. So insert tree. You need the pointer to the tree. Item type X and a parent. Okay. Okay. Allocate new node. What? Okay, I'm gonna ignore that for now. So that means to say that I have a pointer to the tree. So I have a pointer to the tree. And then I have the pointer to the parent. Okay, so if okay, so I need to consider if I hit a null or not. I don't know if it makes sense, but this is what I've drawn. Oops. Drawn here. Probably can't see it, but okay, you can't see it. I apologize. Okay. How do you even begin to write this? So you have a pointer to a pointer. Wait, what's the point again? What's the point again to have a pointer to a pointer so that I have to, oh yeah, so that I have to return anything, right? So I can manipulate that. Ah, yes. Okay. Yeah. Whoops. Okay. Yes. Let me just try this and run into errors. Okay, let's just figure this one out. So, and these are just null. Just go null, 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 null. So if I hit a null, I need to decide to insert it left or right. Okay. So it says here if not null. Oh, if it's null. Okay, so let's just, okay, so if that node is null, so I don't know what that is exactly, but let's just say the target node here. So the pointer to this node. So the pointer to this node. Pointer. Pointer of a pointer. Huh. Okay, if it's null, then I need to figure to put it on the left or to the right. Right? What? X. Oh, okay, yeah. That means I already hit it. So, and I was given a parent. Wait. Wait, what? No, that we pass the pointer to the appropriate left or right node to insert. So the assignment. It's tricky to write this in pointers that I'm not familiar with. Okay. So trees and parent, what's the, how do you then call this exactly? Is there an example that you call this? A pointer L to the pointer linking the search subtree to the rest of the tree. Oh, so this is subtree. And then this is parent. Okay. So that means at first you're given the entire tree and then your parent is what? So I guess you are given, I don't get it. So how do you even call this? Okay, whatever, man. So if your pointer is null, if the subtree is null, and you hit that means to say that you are here. Then you straight away just say that now this subtree is gonna hold that data, right? So P. Okay, so yeah, you define a subtree pointer P, and then you say P item equals to X, and then P left, P right. Left is null, right? Yeah, right is also null. And then your parent would be parent. And then you will say that this goes to P, and then that's it. Okay. And if you're not, you call insert tree, where now you have to point. Okay, well, if your current data arrow item less than X, less than X. If it's less than X, then you go to the wait. If X is greater, then it goes to your right. Wait, is X is greater? Yeah, okay. Okay, then what do you put inside here? You put inside the pointer to the pointer to the right subtree. So now you are pointing, okay, now you're pointing to here. You are saying the pointer of a pointer to this node. So the pointer to this node is dot right of this. Now you need to point to that. I don't know how to do that. Wait, what is this? What? The address of the pointer to the... What the heck? Star L means the pointer to this node. Means this. Its left. Its right will be this, yes. So don't you just... And then the address of this. Wait, star L dot right would be the subtree. So now you need to have this pointing to here. So you're gonna need to have something like star L equals star L dot right. Star L arrow right. And then you pass in star L. Which is this, which is, then you pass L. And then the parent will be just star L. Okay. Okay, one last thing I need to search up here. I'm not so clear with this. Let's see. And then call argument. The value of the pointer function argument double pointer call with address. So the pointer holds the address. Okay, so the pointer which points to something holds the address of this something. So if you are a pointer to a pointer, so you might as well just give the address of the pointer. Right? So is this what's happening here? You give the address, which is the ampersand, of whoops, of this pointer. Okay. So this is call by reference, I guess. There we go. So if I want, you could either give a pointer of X, or you can just give the address. So in this case, let me just make that crystal clear. I have L, which points to a pointer that points to the head. L is the pointer to the pointer L to the pointer linking the subtree to the rest of the tree. Okay. Yes. So so this is dot right. The address of this pointer. Wait, I don't understand. So if I do star L comma right or star L comma left. Oh man, is this one of those C thing that star L dot item, the parent is now star L. Wait, what is this then? Star L comma right is the pointer to this thing. And then you give the address of that pointer. I see. Okay, so the correct picture is not like this actually. Okay, let's make it quite clear. So I have a node, and I have a pointer L that points to something, and this points to here, and the right points to something that points to here. So I want this pointer. Or you can just think about it one layer less, right? I mean, this is the pointer to here, and this points to a pointer of this node. This dot right is a pointer of this node. Okay. Okay. With no children, delete node with no children, like deleting node 0 with no children. 3, and then delete with 1 children, like 6, and then with 2 children, like 4. There's 1 parent and 1 grandchildren, and we can link the grandchild directly to the parent without violating the in order. Yep. We have 2 children. So if I have 2 children, so in this case, if I have 2 children and I want to remove, then I would need to replace myself with, oh no, we need to replace it with the left subtree and put the right subtree somewhere below. We label this node with its key immediate successor in the sorted order, right? This successor must be the smallest value in the right subtree, specifically the leftmost descendant in the right subtree. So yeah, so if I were to delete, let's say this one, I need to I just put this one here. Okay, then everything is intact. Okay, so replace, oh, it's huge. Replace deleted node with leftmost node of right sub. So if there's 1 children, it's easy, you just directly connect them. If it's 2 children, it's a little bit complicated. Okay. I see. The worst case requires 2 searches OH, where H is a height and plus a constant amount of pointer manipulation. Yeah, so if the 2 searches is when you want to search for the leftmost as well. Okay. Yeah, I don't think I can finish all of it tonight. I think I'm a bit too ambitious. But okay. Let's try either way. Perfectly balanced login. But the tree must be perfectly balanced. The data structure has no control for the order of insertion. That's true. In a sorted order, if I insert A followed by insert B, insert C, insert D, it'd be a skinny tree with only right pointers. That's right. If we consider each of the n possible, okay. Quicksort. Quicksort is the one that's the, what is it? The partition one, I think. Or is that merge sort? No, that's Quicksort. I think so. Mm. So you can use a balance search tree to create a dictionary with cost log n. Okay. We can assume the worst case complexities of balanced binary trees to be a fair measure. Okay. Okay. Oh, here we go. Actually, so far this is one of the parts of the book that I enjoy the most. It gives you a problem, makes you think about it, and explains the solution. Rather than one of those full-blown questions in the middle of the chapter, and then you're required to stop and then work half an hour on it. It doesn't make any sense, and most people just skip past it and not get anything out of that. You're given n reading and printing them in sorted order. Taking reading n the task of reading n numbers and just place. Okay, how can you sort O and log n time using only insert and in order? And then printing them out in a sorted order. You suppose you have access to a balanced dictionary data structure which supports operation of insert each in O log n time. So that means to fill up the tree, you do n log n. How can you sort in using only insert and in order traversal? You insert everything and then you in order traversal the entire tree. So that's n log n plus what is it? You put everything in that's n log n, and then in order traversal, which is just search for everything. Wait, in order traversal means then you do it for n log n, right? That's the same. Okay, I think. Should I answer it? Insert. No, insert everything. Then traverse. And this is n log n as well, I think. Because search is how can you sort using minimum successor and insert. Ooh, minimum successor. What is successor? What? Successor meaning the next largest key. The next largest key might not be. So the next largest key is still a search, right? Let me think. So if let's say you have a, what the hell is this? Let's say you have a tree like this, and then you have to find 9, and then you find the next largest value. If it's on the right, if it's on the right, if it's not on the right, then it's the next thing, the leftmost on the right. So that is also n log n. Minimum. Okay, I shouldn't think about this. I should just say insert everything, because everything is n log n already, so I don't really need to worry about. Dude, Foxy Reader is weird, I swear. Okay, sort in n log n using only minimum success and insert. Insert everything, find minimum, then successor, repeat. Insert everything, find minimum, delete it. Okay, we search. Oh, it's like that, okay. So initialize tree, which is insert everything, read and insert. Wait, I'm confused. Insert where? Insert into tree. Right, so you insert everything and then you traverse. So this one is insert everything, minimum, find minimum, and then find the successor. Yeah. Delete and then find the minimum. Okay, so there's no search exactly. Yeah. Yeah, okay, cool. The key to is to treat them as black boxes. I think that's a good idea. That's a very good tip, because if I start thinking into the details and I just get confused and I lose sight of the whole point, is that if I can pack everything into log n, all I need to do is to figure out how many logins do I need to do, and then just work with those as a kind of unit operations. Okay. How are we doing on time? 42 minutes. All right, let's keep on going. Insert new job into a priority queue. Okay. Given an item X with key K, insert it into the priority queue. Key K. Wait, let me just check something here. When you say key, mm. Key. I'm confused as what they mean by key here. The smallest key must recite. So key is data. But what about... Okay, then what's the point of calling it a key? Yeah, okay, key. Uh... Wait, but then they said something about dictionaries, right? Yep. Yeah, here we go. Hmm. Okay, I think in this, so key and data are the same thing, but it's just in the context, right? So key, yeah. So look for key and then insert data with, and then so X has the key of X. Yeah, maybe I'm not thinking this correctly. I'm not sure. Given data item X, add it to, give it a pointer and a given data X. Move it from D. Given a search key K, return a pointer to the element whose key value is K. The hell's a key value? Key is key. What? Okay, but I guess in this case it's the same. So that's how I understand it so far. Okay, keep on going. Okay. Uh, 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 uh. Let me go to the washroom. Okay, I'm back. Alright. Okay, let's keep on going. Insert key. Okay, so item is node, key is the value. Uh So in this case, yeah. Okay, yeah. Okay, delete. I mean, this one so far doesn't tell me anything. It's just super high level. Single people maintain. Ah, okay, so priority queue is just about maximum minimum. I see, okay. Single people maintain a priority queue of potential dating candidates, mentally if not explicitly. One impression, attractiveness, desirability score. Desirability serves as a key for inserting this entry into a little black book priority queue, and then you just extract the most desirable. Fair enough. Spending an evening to evaluate them better and reinserting them to a priority queue. So a priority queue really is a ranking, right? That's all it is, right? I guess you can think about how to model it properly in a data structure. I guess what that means is when you insert it, you want to be very smart about it, right? So that it's a bit like playing cards, right? If you have a bunch of cards and you have a new card, you just find where's the next, where it belongs, so you slide it and everything. And then whenever you want the largest, you just pick from the rightmost or leftmost or something like that. Okay. Okay. Stop and think. Let's do that. Basic priority queue. What is the worst? Okay. What is the worst case time complexity of the three basic priority queue operations? Insert, min, max, find, and delete. When the basic data structure is okay. So let me take a guess here. If it's unsorted array, insert would be O1. I mean, insert is just O1, right? And then find minimum. It's N because you don't know. And then delete. Delete is N, but can use constant time trick. Okay. If it is sorted, wait. So insert would be log n. Log n plus n actually. So it's actually n. Because you have to shift everything back. And minimum would be log n. Delete would be log n plus n as well. So that would be n. Okay, let's keep on going. And a balanced binary search tree. To insert, it is log n. Find, it is log n. And delete, it is also log n with some constant terms. Ah, is that what it is? I'm not sure. Insertion and deletion in constant time and search minimum. A linear time implementation of delete. Find minimum followed by search and delete. Wait, I'm confused as to find minimum versus search. What does that mean? Don't you need to search to find a minimum? Wait, return a pointer to that respond. Okay. So you just find the pointer and then you search for that point, look for that pointer, and then delete. We can implement search, insert, and delete in linear time and minimum in constant time. Wait, constant time? Oh. It's just one. Of course, it's just the leftmost. Whoops. delete minimum. Yeah, okay. Oh, okay. So linear. Yeah. All particles deletions only involve the minimum. By storing, then you can always make it the last one. Okay. Okay. Uh, to constant. Okay, and if I don't know what this means in like 2 months, I'll just reread it. And then binary invert. Wait, find minimum. Wait, find minimum is just. So 1 1. Wait. Unsorted array. How do you find minimum? How do you you can use the same trick, right? The Okay. And then we have n1 n1 I can use 1. And then wait, balance binary search tree. Why is it 1? Wait, insert is log n. Find minimum and delete minimum. I'm not sure. Why is delete minimum 1? Yeah, how do you even do? What? We can delete the minimum entry have. What have? We have? The honest find takes linear time and unsorted array. Can be folded into the cost of deletion. I see. So I guess I can say here that can track the minimum and delete it at constant cost. So the cost here is to okay. Okay, yeah. The heap. Suppose we partition the triangles into strips of adjacent triangles and walk along the strip. What does that even mean? What's a strip? Strips of adjacent triangles. See, I don't know what it means. What are strips of adjacent triangles? Like this? I don't know what. We partition into strips. Okay, I assume like, so what, this is a green strip? A triangulated model of a dinosaur are several, wait, I think several triangle strips in the model. Huh? Okay. What? Oh wait, what is, shoot. Wait, is my mouse suddenly powered out? Oh shoot. Hmm. Wow, no battery. Okay, let me see how I charge it. I think, let's see here. Oh no, is it just suddenly? Okay, let's give it charge a minute. Let's keep on going. Since each triangle shares two vertices in common with its neighbor, we save the cost of retransmitting the extra two vertices and associated information. Ah, I see what you mean. So that means you think about moving from triangle to triangle, and each time you report one new. All turns alternate from left to right. What? Partitioning in triangle strips with left turns with the flexible of arbitrary turns. What? So this is right, then go to your left, then go to your right. I see. Okay. Okay. I don't know what this has to do with anything. I mean, this looks like an interesting story, but at this point I can't really appreciate it. Like dual graphs and Hamiltonian path, like it's a graph theory thing, and I'm just gonna. Okay, fine, I'll just read it. Even though I don't really know what I'm reading. We knew not to look for an optimal algorithm, but concentrate on heuristic. For strip cover would start from. Wait, what's the task again? We save to make the description of the triangles unambiguous. Okay. The task of finding a small number of strips that cover each triangle in the mesh. The task of finding a small number of strips that cover each triangle. What does that even mean? What do you mean a small number of strips? What? Okay. I mean, there are many strips, right? There's like whatever combinatorial answer you can come up with. Okay. And an edge between each pair. This dual graph captures all the information of triangulation and needed to partition it into triangular strips. Okay. Once we have dual graph available, the project will begin in earnest. We sought to partition the vertices into as few paths or strips as possible. I see. Partitioning it into one path implied that we had discovered a Hamiltonian path, meaning to say we can cut through all the edges, which defined by visitation exactly once. Oh yeah, that's true. Wait, is it? Why is it vertex? Ah, that's true. Okay, but this has nothing to do with left, right? Ah, okay. Since finding Hamilton is NP complete, we knew not to look for optimal path but concentrate on heuristic. The simplest heuristic for strip cover would start from an arbitrary triangle, do a left-right walk until the walk ends, either by hitting the boundary of the object or previously visited triangle. This heuristic had the advantage that it will be fast and simple, although there's no reason why you should find the smallest possible set of left-right strips for a given triangulation. That's fair. The greedy heuristic would more likely result in small number of strips. Greedy heuristics always try to grab the best possible thing first. In the case, would be identify starting triangle that yields the longest left-right strip. But how do you even know that? So you just do it for every one of them? Identify the starting triangle that yields the longest left-right strip and then peel that one off first. Fair enough. Yeah, exactly. Let k be the length of walk possible from an average vertex. Repeating this for each of the roughly and divided by k strips. Wait, what? Using the simplest possible implementation, we could walk from each of the n vertices and then be the length of walk possible on average. Repeating this for each of the roughly n divided by k strips, we yield about n squared, which is hopelessly slow. We'll peel away. We have used the bounded height to update the queue entry. Quickly find where it was. Mm-hmm. Okay. Oof. Triangle count greedy cost. Yeah, so greedy is good. It's naive. Uh, Store the strips according to the length. The next strip to peel always set on top of the queue. Okay. The priority queue had to permit reducing the priority of arbitrary elements of the queue whenever we update the string length to reflect what triangles were peeled off. Okay. Wait, what? Total size of the strips. Is our priority queue data structure. Okay, hashing. Let's keep on going. Size of the alphabet on which a given string is written. Let char c be the function that maps each symbol of the alphabet to a unique integer from 0 to alpha minus 1, and the function maps each into unique. Okay, by treating like digits. Okay, base alpha. Yeah, okay. Alpha to the s minus I guess as a +1 somehow, or because you have a -1. Do you know? Wait, because it starts with 0. Wait, what? Hold on. So the first one should be 0, right? So minus. Wait, S is the string length of the string. So if your string has 5, then that means your first letter is gonna be your 0, 1, 2, 3, 4. Ah, okay, yeah, so 4. Okay, I see. So to the power 4, 3, 2, 1, 0, char. Okay, so it is exactly base alpha. Remainder H. What is H? Oh, H, okay. Mod M. M is just the number of the length of the size of your table, I guess. M is a large prime, so not too close to 2i minus 1. Not too close to 2 to the I minus 1. Okay. Okay, yeah, I get the basic idea of hashing. You distribute it, and if you clash, then you like do something with it. Yeah. Chaining. Three 3.9. Yeah, okay, so you just stack them behind each other. Hmm. Okay. Uh okay, keep on going, keep on going. Come on, come on. Oh, so stressful. Okay. Okay. Alright, keep it together and push. Okay, chaining is the easiest. To represent the hash table as an array of m linked lists. The ith list will contain all the items that hash of the value of I, thus search, insertion, delete will problem in linked list. If n keys are distributed uniformly, each list will contain roughly n divided by m elements, making a constant size where n roughly equals to m. Each list will contain making them a constant size. Constant size? What does the constant size mean? I mean, if m roughly equals to m, then it would just be 1, right? Shouldn't it be like maybe by some multiple of n, then you get constant? Okay, whatever. Okay, yeah. But the votes are considerable amount to the pointers, yes. Okay. The alternative, open addressing, hash table is maintained as an array of elements, not buckets. Each initialized to null as shown in 3.10 on an insertion. We check to see if the desired position is empty. If so, we insert it. If not, we find something else to insert instead. Okay. The simplest possible sequential probing. Search inserts the item to the next open spot. That's fair. If the table is not too full, the contiguous run should be fairly small. Hence, location shouldn't be a few slots away. But how do you look for it though? Because you look for it and then how do you how do you know to go back? How do you know to find it again? Ah, if so, return it. Otherwise, we must keep checking through the run. I see. Okay. Yeah, I probably read about this some years ago, but yeah, okay. So one is that you just stack them up. Other is that you just do the next best thing, and then you have a bit of a cost here. Oh, deletion. Ooh, wait. Yeah, because for linked list it's quite straightforward. The idea, right? You just delete something like either the head of the list or something like that. Might break a chain of insertions. Mike, since removing one element, might break a chain of insertions. So let's say you remove this one. Wait, what? How does that make any sense? It might. Uh, OM to initialize an M element hash table to null elements prior to the first insertion. Traversing all elements in the table takes ON plus M time. Why? Wait, what is N? Isn't N like the number of things you need? N keys, right? And M. Traversing all elements in the table takes ON plus M times for chaining. Chaining, because we have to scan all M buckets to look for the elements, even if the actual number of the inserted item. What? We have to scan all M buckets looking for elements, even if the actual number of inserted item is small. Wait, I don't get it. What? Huh? Wouldn't it? Wait, why isn't it N? Oh, because you need to visit everything. So if it's like this and then like this, you need to visit this. And then need to visit this. Wait a second. Takes. So a lot of them will be wasted. So this might be m. So m plus m. Okay. 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 For open address, it will be n. OM. Since n must be at most m. Yes. The dictionary operations for n items can be implemented in the following expected worst and best case. Wait, what's the difference between doubly and singly in this case? So imagine here now you have a doubly linked list, which means you can bounce back and forth. I mean, okay. So it's m plus m lah. But if it's singly, it's still m plus m, right? You can just keep track, right? Not sure. Search for a key. For chaining, right? For chaining with doubly linked list. Worst case is O hash table. For n items. The worst case is that they are all in the same line, right? It's n. Expected, it is n divided by m. Oh my god. Insert. Insert is O1 because you just insert at the front. Delete is O1, you can just delete from the front. Successor. The hell does successor mean? Meaning the next. What? What is a successor? What would a successor mean? The next largest key? So let's say this has key 5 to look for 6. You need to look through the whole thing. Can't you put it? Wait. Maps keys to integers, right? So successor is the next largest key. This one is looking through the whole thing. Yes, I agree. Successor. So let's say I give you an item with a key 10, then I'll find 11. I'm gonna search for 11, right? Why isn't it? What? What? Wait, what does successor mean in this case? Hash table. What? Oh yeah, oh my god. Exactly the same book. Doesn't find successor in searching the next element. Yeah, exactly. Hashing achieves constant time search at the cost of destroying order. When I search for an element, I hash it all and then look for the chosen bucket. Worst case, if I scan linearly. And when I want the next element given, I have no guarantee that it will be in the same bucket. In fact, I have no knowledge where it is, since I do not have do not know what the successor is. Oh, ah, okay, correct. Okay, sales. Oh, geez, the heck. Okay, strings or sequences of characters. Strings are. Mm-hmm. Wait, I don't understand. It checks whether the pattern's character matches the corresponding text characters. Why is this? Shouldn't this be at most size of T? Page 43. Uh, The inner while loop goes around. Oh, because I see what you mean. Because you gotta check. I see. Okay. All right. Okay, I see. Hmm. Okay. I see. N minus M. So we just hash everything. We hash M times. No, I mean like something like, you know, F N minus M, right? Plus 2. What is plus 2? Oh, plus the itself. Windows of T. Wait. Uh, okay, yeah, so plus what should be a very small number of OM time verification step. Okay. How many more pages are we? Oh, we're almost done. Okay, okay. Then we are down to practicing. Okay, so yeah, we can finish this. We can do this. Okay. Apply to the M character starting from the J's position of string S. So from J's position, okay. What changes if we now try to compute Sj plus 1, the hash of the next M window characters? Note that M minus 1 are both in the same window, although this differ by one number down. The algebra shows that we can just add that difference. Yes. This means that once we know the hash value of the J's position, at the cost of two multiplications, one addition and one subtraction. This can be done in constant time. The value of alpha M minus 1 can be computed once and used for all hash value computations. Okay, hold on, let me think. If we do it J plus 1, it will be, yeah, char, it will be shifted. Yes, so you take one multiplication and then like a, yes, so it can be done constant time. This math works even if you compute mod M, where M is a reasonably large prime, thus keeping the size of our hash value small. I see. When even the pattern string is long. Rubbing cup is a good example. So okay, so the goal, so let me just summarize this. The point is to hash the substrings, and we note that naively it costs OM to hash string of M characters, but we can cut that down to O1 because we use relevant information. We can modify the previous hash. Okay, cool. All right. Uh, let's see. I don't know. What the Holy. Uh, uh, Okay. Hmm. Uh, uh, yeah. Okay, okay. Hmm. Hmm. Uh, ha 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 ha. Wait, what am I doing again? Oh, sorry, I was distracted. I was talking to a friend. Okay. Yeah, yeah, yeah. Mm. Mm. If I is in the subset. So 12, 12, 12, 12. Wow, so chapter 12 seems it's pretty important. What's chapter 12? What is chapter 12? Wait, I could just look here, right? Haha, I'm stupid. Oh, okay. Uh, Data structures. Okay, so okay, yeah, yeah, I see. Dinner in the first place, will anything be open? Oh my god. Tired. I'm tired. Okay. Algorist. Is that a word? Algorist? No way. Algorist. Algorithmist? 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 Algorithmist. Algorist. Dude. Uh-huh. Shortest common superstring. Shortest common superstring. Okay. Concatenation of two fragments can be in S only if all subfragments are... Dude, there's a lot of errors in this book, huh? Yeah, okay, let's just quickly read through this story. It looks fun anyway. So DNA represented by JTC, string matching, cranial problems such as shortest common superstring. DNA sequences are very long strings. Human genome 3 million base pairs means they're asymptotic, usually justified. I see. Enough money is being invested in genomics to claim their piece of action. Okay. One of my interests revolve around proposed technique, DNA called sequencing by hybridization. This procedure attaches a set of probes to an array, forming a sequencing chip. Each of these probes determines whether or not the probe string occurs as a substring of the DNA target. The DNA target can now be sequenced based on the constraints of which string and are not substrings of the target. Okay. Right. We sought to identify all the strings of length 2k that are possible substrings of an unknown string S, given the set of all length k substrings of S. Hold up, let me read that one more time. We identify all the strings of length 2k that are possible substrings of an unknown string S, given the set of all length k substrings. Ah, okay. So let's say S is 10k, and then we want to find all length k substrings. So and then we want to find all the 2K. Oh, that should be. That should. Wait, see the templates. I see. Redemption. Mm-hmm. 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 If you know the ACC and CC are the only length to a substring, then ACCA to be a substring, since the center substring is one of our possibilities. I see. However, CA cannot be because A. I see. To construct all the consistent. Yes. And it has to make sure that they all span. Would find the correct string within n log n comparisons, where each comparison involved testing of which of two appeared first in alphabetical order. The total time is k log n. That seemed pretty good. So my graduate student used the binary search tree, worked great up to reran it. It worked great up to the moment we ran it. I tried the fastest computer we profiled our program and discovered that almost all the time was spent searching. If you did this k minus 1 times for each, we need a faster dictionary data structure since search was the innermost operation in such a deep loop. How about using a hash table? I suggest that you should take OK time to hash a k string and look at about table. That should knock off a factor of log n, which should mean something as n equals 2000. We should have expected. After all, log 2000 is just 11. We need, but what can be faster than hash table? Sure, it takes k comparisons to test the first substring, but maybe we can do better on second test. Remember where our dictionary queries come from. When we concatenate A, B, C, E, F, G, the first testing whether B, C, D is in density E, F, these strings differ by only one character, so we'll be able to exploit this. Take constant time. The second key is not going to be near the first. The binary tree won't help, since A, B, C differ. The two string will be different parts of the tree, but we can use a suffix tree to do this. Is a tree containing all the suffixes of a given set of strings. Okay, I'm not really following, but I just read it for the storyness. Mm. Cool. And we are done with the chapter. Okay, of course, there's still all the practice things that I'm not really. Maybe I'll spend one other day doing it. I don't know how far I can get because this looks. For full credit, identify the position of the first offending parenthesis if the string is not properly nested or balanced. Oof, this looks pretty intense. But okay, cool. So today I learned about the kind of the subtleties of hashing, which conceptually it's a very simple idea, but when it's contextualized in some of these applications, then you can see how important it is. Some of these minor issues seem to yeah, how important they are and how much they seem to matter. And binary search tree, balanced search tree, chaining, and open addressing, and then so things like strings, and then yeah. Okay, cool. All right, pretty happy I did that. All right, it's 1 a.m. Maybe I'll do some more work and I'll head to bed. All right. See you guys around.